Welcome to xTalk. My name is Molly Ruggles. I'm in residential education at the Office of Digital Learning, which is part of the Vice President's Office of Open Learning. Today we're thrilled to host Kyle Keene, a lecturer in the Department of Materials Science and Engineering, as well as joining him will be Andrew Ringler, Mark Bratlick, and Ian Kim Riley. I have a few announcements before we start. You may have noticed we're videotaping, and this event will be posted publicly, so if for any reason you're uncomfortable being in the video, just sit towards the back and you'll be okay. I'm passing around a clipboard. It really helps for us, for you to sign in. It helps us know who our audience is and how we can better serve you and better give you better programming, so please do sign in. It also puts you on the mailing list for xTalks and residential. If you're not already on it, and if for any reason you don't want to be in the mailing list, just indicate that and we'll leave you off. We have 2 xTalks coming up later this fall. It's probably hard to see the print, but December 13, Claire Pepimenian on microphenomenology, and then December 18th, Professors Lorna Gibson and Wolfgang Ketterle, who are both faculty innovators. And you can see more about those programs on the ODL website if you're interested. Videotaping and signing in. I guess Kyle will talk about our programming. We're aware of a memorial service for President Paul Gray, so we're going to make sure that people can go to that if they want to. So without further ado, please join me in a warm welcome to Dr. Keene and his team.
Well, thank you very much for coming out. And yes, we will end with plenty of time for you to interact with the system as well as get to the memorial service, so don't stress about that. We are going to be talking about interactivity and connectedness in the classroom and how we facilitate that. So if PowerPoint will cooperate. All right, so we are housed in the Materials Science Department, very happily. We like to call ourselves the Interactive Materials Education Laboratory. Inside of the lab, we do things like teach students how to build little visual interactive simulations that help communicate scientific information. We are extremely grateful for the Europe office and the MIT SUTD collaboration, which helped fund some workshops that we're going to talk about. And very, very grateful for all the Office of Digital Learning's support, or Open Learning, I think it is now rebranded as. I need to update that slide. So I am Kyle Keene. I'm a lecturer in material science. I've been there for, I think, about 3 years. And I'll let Andrew introduce himself.
I'm Andrew Ringler. I'm an interactive artist and teacher. Teach at Mass College of Art, as well as with Kyle at MIT. And help with some mentoring of Kyle's students at MIT. I'm also currently teaching at Lesley University.
And everything that we get to do is made possible by Professor Craig Carter, who has been extremely supportive and an endless source of creativity and inspiration. So, some subjects that we teach. 3016 is computational methods for material science, where they're building little simulations that are showing diffusion limited aggregation and phenomenology like that. We do a seminar for freshmen about making that's related to material science, and this year we're also piloting one about computing, your first year physics. In IAP, we like to have a little fun and get a little divergent from our normal careers, and so we work with Arduinos to teach students how to build fun and flashy things, as well as the thing that we'll focus on during this talk, which is video game design using the Unity game engine and the Microsoft Kinect. So this will be the main point of our talk, and that all started with a Europe, and I'm going to demo. Let me get rid of the sound. So this is the big picture of what we're going to be talking about. So our Europe, Mark, who will introduce himself in a little bit, built a system. This is gas particles flying around inside of a box. His hand is able to inject or remove heat from the system. So the big idea would be walking down the infinite corridor. You can walk in front of every lab, and everyone has published some version of their research where you can come up and start interacting with something so you can understand what they're doing. That's what I would love to see, is kind of hallways become interactive art. We took that Europe project and opened it up. It's fairly simple to teach people how to create games and simulations for that system. So during IAP last year, we got some funding and ran a 9-day workshop, and then spent the next few months publishing it on OCW. So there's videos of student projects as well as all of the lectures that we gave, which were very few and far between. We don't lecture very often because it's very project-based. And so I'm going to let this play for about 2 minutes and show you the results.
I'm Darius Boss.
And I'm Kaylin.
And our project
Thanks.
was kind of a mini RPG, I guess. Escape from the Zoo. Right here is like an opening cutscene. So there's these cute little animals, and they're going to try and escape the zoo.
Yeah. The premise of our idea was that we wanted to have different animals that you could control that each had different ways of moving with the Kinect, and we wanted the ways of moving to kind of, I guess, connect with the ways that the animals themselves move. So we have, the gecko and the frog who move very differently, the penguin and the rhino. So we have 4 different types of controls that correspond with each animal.
I'll jump to the game.
So the controls that are universal is if I stick my left hand out, I'm going to turn left. Okay. If I use my right hand, I'm going to turn right. So now the penguins move a book.
Oops.
Knocking things over. But it's actually going to be a little slow and gimmicky. Originally the idea for the penguin was to kind of go like this. Which actually still kind of works, which is great. Because that way you kind of waddle in the penguin, right? However, it kind of got hard because the shoulders were really close to each other. So in the code it would be like if one shoulder is in front of the other, and because they're close, we switch it to the hands. So you can see I'm very loose with my hands just because it helps with the code.
So that's an example of the outcome of what the workshop produced. And I like that little clip because it shows him talking about the algorithm behind the interaction as well as the story that he wants the person to inject themselves into. And the connection to science here would be for kids to be able to do the frog, you had to crawl like a frog who was kind of going through some dirty mud. The penguin, you had to wiggle around a bit. So it's something to allow somebody to embody some aspect of the creature that they are interacting with and trying to control. So yeah, that's the big picture. If you tune out for the rest of the talk, you've gotten the big picture. The rest will be a bit of me on the soapbox talking about how to run a class like that. For the recording, I wanted to put the links up there in case anyone wants to find other project videos as well as lecture videos. So I'm going to talk briefly about what the Unity video game engine is. I'm going to let Andrew actually introduce really high level what the Unity video game engine is and why we use it.
Sure, yeah, so it's a professional software package that lets you create video games mostly, 3D video games. This is a view of what it would look like as a programmer. So you can see a preview of the game, you can see your various assets to create the game, game objects, and on the right there's like properties of a game object. So it's basically a view of the game. You can drag and drop various aspects to program, as well as actually type in code into scripts. And for the purpose of the class, Mark will talk about later, we actually hooked up the Unity game engine to the Xbox Kinect sensor, which is a 3D depth sensor that allows us to actually put gestural interface into the game engine.
So clear objectives are to have students use the Unity game engine. They're there because they want to learn how to make a video game, so we need to teach them the skills to do that. I want them to understand when it is the appropriate tool and when it's not the appropriate tool. To connect, since we only have them for 9 days and the Unity game engine is used by huge video game production companies, we can't make them experts, but we can connect them to an extremely great online resource bank of tutorials for them to learn skills if they want to. To practice collaboration, we had students coming from Singapore as exchange students who are part of this class, so we wanted to have explicit communication training as well as practice, and then strengthen storytelling abilities, because I am just a huge fan of storytelling as an endeavor for humans. And the thing that I think a lot of classes should also consider are experiential objectives. What do you want the student to experience during the course? I want them to have fun, maybe even laugh. The video showed I got the successful laugh. Embrace gentle creativity as a means to overcome perfectionistic ideals, to experience community and interaction, to learn when to purposefully fail and how to take skills out of a failure, and to value oneself as a learner. So these are larger ideals that I like to keep in mind when I start running classes. The structure of the class is not as much talking as I'll even do today. It's about 20 minutes on some topic, some technical skill while I demonstrate. 40 minutes where they then take the Unity game engine and do it themselves. 20 minutes where I'll bring them back together and do a group ideation session or something like that. And then 100 minutes to let them build the skills. So it's very much in that interactive and self-paced kind of classroom. What that ends up looking like is a very dynamic class where tables are being moved, and I'm at the board there, but I'm not even lecturing. I'm helping to model ideation. So they're giving me ideas, and I'm writing ideas up on the board for them to self-organize by interest. There's group work where they sit around, and then there's creative work where they form small groups and break out, even leave the classroom and go work with their group for a bit. So it's definitely not a traditional lecture setting. The next, the kind of the tail end of this, we're going to talk about organized in the same way that the OCW is organized. The OCW resource has much more detail if you want to learn about it. The kind of what I call the anatomy of the workshop. So students have to get started. We need to get them up to speed in communicating. We need to get them technical skills. So we give them a guided tutorial. We need to show them that in order to be a creative technologist, you can sometimes just modify small things that you know how to do, and that qualifies as creativity. You don't have to be a completely original thinker. We want them to learn how to collaborate, and then do a project which they're going to fail on, and we tell them they're going to fail, and we tell them how they're going to use that failure to learn, and then we have them form groups and do a project that they should succeed at. And you saw the result of the successful project. So getting started, I'm going to have Andrew talk about what we do to get students up to speed in the classroom when they show up from Singapore. There's people who are alumni from MIT, as well as people who are graduate students, as well as freshmen. Everyone showed up in this class, and we needed to get them talking.
Yeah, so here we're actually getting the group in a circle doing an improv exercise. So we borrowed techniques from improv theater, improv comedy. They have a whole set of exercises they do to help them prepare for performing on stage. And a lot of these exercises are really appropriate for the classroom and helping people prepare to talk or collaborate or lower their inhibition. So some of them are just really silly physical exercises, like throwing an imaginary ball. Some are like just talking exercises, word association. And so we started most of the classes with some like really short improv exercise or name game, just to get people communicating.
So the next thing we need to do is build technical skills, and we, as much variation as we have in age, we also have in skill level. So the students come in, some of them know Unity and they just wanted to spend 9 days working with other people to build a game. Some have never used it and are business majors and really just want to learn. So on the first day, there's a guided tutorial, and the way that you run that is you take everyone who has never used Unity and you put them in one place. You take everyone who has, you put them in another, You tell the people who have no experience to form groups because they're going to go through a guided tutorial together. And the people who have experience, you inject as mentors into those groups to serve as peer instructors. That way everyone is engaged, everyone gets to learn, everyone feels like they have something to contribute. And it seemed to work very well. So the instructor would take their computer and run the tutorial and pause it every time that a task was given to the person who's supposed to be watching the tutorial. Everyone would have to complete it. I explicitly tell them, if you are confused about anything, then say something. And if you're nervous to say something, then say, Kyle told me I'm supposed to say something. And that's perfectly acceptable as long as you pause it so that you can understand what's happening. And the students were extremely receptive to this type of model. So yeah, this is the get them technical skills in a really short amount of time, also starting to build collaboration and vulnerability by admitting when you need the group to stop so that you can ask a question.
Great. And so, as we mentioned, Unity Game Engine is this professional environment for creating games, and so there's this rich ecosystem of resources available online. So in the guided tutorial, that's not something we created. It's just out there available for free, and there's dozens of other great ones that people can learn from. So beyond just kind of following these step-by-step instructions they see online, we want them to say, how do we create something else from that? So now that we've created this program, we're trying to frame creativity as modifying what you have. So they've created this program just by following a tutorial, but then what if they change the colors of the game? What if they change little numbers in the code that tweak the size of things, or the number of objects that appear in a game? We're sort of framing this as creativity. So expanding on what you know, just a slight variation, then becomes something of your own. And so in art, that's known as appropriation. It's a form of creativity. It's a form of generation of ideas that we want to promote. And I think it's very useful for technical skills, because trying to start from nothing is extremely hard and is not usually useful with technical skills or a new programming language. So that's what we're trying to reinforce in this expanding on.
So the next thing we need is they have built skills. They've learned how to be a bit more gentle on their expectations of themselves and their creative force. And then we want to help them collaborate. So one way to facilitate this that we do is to stand in front of the class and ask for ideas. And every time somebody gives me an idea, I model constructive excitement as well as feedback as well as modification. So they give me an idea and they say, that's amazing, I like that. I'll write it on the board. I'll say, does anybody else have any modifications that might be interesting off of that, variations on it? If no one does, I seem to always have some variation that I can come up with. So I'll write down a variation and say, I really like that. I like that so much, it brought some inspiration into me, and I wanted to make this small variation. So I just explicitly do this for about 20 minutes, and we end up with chalkboards full of things. And then we tell the students, find the ones that have piqued your interest, and go walk over next to it and put your initials in it. And we're going to see if we can find some way to group students by interest so that they're going to work on their project. So it's a very hard thing to have students within 4 days become teammates and start to work on a project. And if you can start by having a really clear indication of what your shared interests are, then you can start them running and they don't have to worry about navigating that initial ideation phase without having any explicit training in it. So the kind of facilitation of collaboration is very important. This is a great moment. I absolutely love this picture. It's such a, somebody took a perfect picture at that moment. After they collaborate, they are then told, you're going to embark on your craziest, most creative idea, and your purpose is to fail. Your whole thing is not to try to build this crazy imaginative game. Your purpose is to come up with the craziest thing you can do and then just try to do it as best you can and know that you're going to hit snags at every step. And this is exactly what you're supposed to do. So failing here is failing to produce the game, but in fact you're purposefully going to find all of the edges of the system that you're using and all of the roles in your teammates and how to collaborate with them that you're going to need in order to succeed on the next project. So removing this intense fear that the first idea that they have, they need to be able to build, and it needs to look as good as something that could be published on the web. You have to absolutely deconstruct that and let them know, this is the time to go completely crazy. None of us know what the boundaries are of the system. Let's get our hands dirty and find those boundaries by taking on a project that's just too big to even possibly finish. So this is, I think, a very helpful task in order to let people know what they need in real teammates, what skills they actually bring to the table, what skills they need to recruit from other people to join their group, and as well as allows people to not have to feel like they're going to be committed for 5 days to working with people that they don't know. So you can try a group, and if it doesn't work either creatively or you don't have a shared vision, then this is a moment when you can then switch very fluidly to go to another group and work with somebody else. So that's this short project where they're designed to fail.
Right, and so we've gone from a tutorial, just following technical skills, to expanding on a tutorial. So still following technical skills, like taking inspiration from the code, to here, they're actually taking their first idea. This is what I want to accomplish. I'm not going to, there's not enough time. How do I pull in what I've learned from the tutorial into the short project and fail? Successfully.
Successfully, yes. And then the hope is they're all ready to get really serious, spend about 4 days with a new group, possibly a new group, to build a project that every time we do this, they end up re-scoping their project from the initial one, and they go, oh, I can't do that thing, I can't do that thing, I think we could achievably do this. So they instantly demonstrate this ability to take what was this grandiose idea and then figure out what's actually achievable in 4 days. So this is a really important skill that if you're not taught it and you don't experience it, then you have no idea where the boundaries lie about how to plan projects and work with a team to achieve them. Anything else about the long project?
Right. No, exactly.
All right,
yes.
Cool. Yes, so you saw an example, which was the zoo game, where you have to embody 4 different animals in order to accomplish goals, and that's one example of the final projects. And at this point, I will hand it over to Mark, who can either talk about the other projects that came out of the class, or you can switch and demo your system.
Sure, let's not go to the system yet, because we haven't even introduced what that is yet, right?
Oh, there's the little video. You want me to go back to the video?
No, it's good.
Okay.
So, other projects that were done, there was one that was, they called it Jedi Ball. And it was like bowling, but you steered the ball by rotating your head, and you made it go faster or slower by thinking harder. They used an EEG headset to monitor that. It was really cool. Similarly, there was one, they called it Totoro, and it was based off of a scene from the movie My Neighbor Totoro, and it had you jumping to grow the tree and making the motions that made it grow in the movie. So what inspired all of these Unity and Kinect lessons was a year off that I started doing my freshman year, and what it was aiming to do is create interactive material science demonstrations using the Microsoft Kinect. As Kyle alluded to earlier, the idea being that we would install it in the infinite. And so we have that system here.
Do you want me to show the video?
Yeah, if you have that video. And so basically we've been working on this system. This summer we had Ian Riley right over there, who also helped build some simulations for this system. And yeah, we're going to demo it today. So this is the Heatsink Simulation. And in this, you control a spot of variable temperature. You can add or subtract energy from localized areas of the system and watch it diffuse throughout the rest of it. So yeah, can we switch over to the HDMI on here? Most secure password in the world. And this is what it looks like now. So you control it with your right hand, and you can like press on the various buttons. It's like designed to be very intuitive. And so we have a variety of simulations. We have material science simulations. We have physics simulations. And then we have PhET simulations, like from the University of Colorado. And so these are just online simulations where you can interact with like the web browser or anything that's HTML5 just using the Kinect here. It makes it so it opens up a lot more content to us, and ultimately enables us to port over other simulations that are already made rather than designing everything from scratch. Yeah, here's the Heatsink one that was mentioned earlier. And as you can see, I can move my hand close. I'm causing the particles to stop, and it like takes energy away from the whole system. Or I can like move it back, and it adds the energy back. Here is molecular dynamics. So molecular dynamics is how particles like arrange themselves in a lattice. So they observe the Lennard-Jones potential, and what the Lennard-Jones potential dictates is that there is this region of lowest energy between two particles. Where it is like stable. So if it is further than that, the particles are attracted to each other. But if it is closer than that, the two particles are like pushed apart very strongly. And so it creates this area of equilibrium in between it. And by having a bunch of particles all governed by this, you create a lattice. And so what you can do is this is without any Lennard-Jones potential in effect. But then when it does go into effect, they all arrange themselves here. And so I can go and I can like grab one of these, and you can observe how it interacts with all the others. Yeah, that one wasn't quite working for some reason. Yeah, Dean, would you like to show yours?
Yeah, sure. So I'm Ian Riley, and I'm a high school senior who's basically brought on to this over the summer. And what I basically did is I created 3 more simulations for this whole project, physics-based simulations. So the one that I'm going to demo for you guys is a pretty simple concept. It's basically, so you can create positive and negative charges that interact with both each other, and a large static positive charge in the middle. So I can move the cursor around with my right hand, and by raising or lowering my left hand, I can spawn a variety of different, or I can spawn either positive or negative particles, basically. And with this, you can see how they both interact with each other. They get stuck on each other because they're attracted to each other. But in the end, the large positive charge in the middle overpowers all that. So with this, you can get some pretty cool stuff going, like just a variety of forces coming. And what this basically is the forces that dictate this are a lot like gravity. So you'll see that the closer I am to it, the more it pushes it away, and the faster it sucks it in. Whereas over here, there's not much force going on at all whatsoever. Another cool one, which is a little neater in my opinion, is you can control positive charge with your left hand, and there we go. So you can, with your left hand, you control the positive charge, and with your right hand, you can spawn negative charges. And with this one, you can just kind of play with it so you can see directly how the forces influence the negative charges based purely on proximity. And the last one that I worked on, or that I made over the summer, is still in its early stages. It's not completely bug-free yet. But what it is I basically tried to emulate what it would be like to launch a satellite around the Earth. So right there, that little gray thing that's the satellite itself. That's the moon. You have the sun way off in the distance. And you can launch it. And the gravities of the Earth, the moon, and the sun way off in the distance all affect the satellite. So over time, you can see that the satellite will change its orbit based on those factors alone. You can get another one, and fire it in another trajectory, and then get a completely different answer. Yeah. They don't exactly crash into the Earth yet, so I'll need to add that in. Yeah, you just make it way over there, launch that, goes way over there. And so you can just visually see how they interact with everything, and that's pretty cool, in my opinion. Back to you, Mark.
Yep. So I think that's all we have. At this point, we will have the system up here. Feel free to interact with it, play with it, ask questions. I hand it back over to Kyle.
Yeah, so that is the presentation portion of the presentation. At which point you can eat cookies, come play with the system. We can take questions if anybody has some quickly, and then you will have plenty of time to get to the Paul Gray Memorial Service. So, yes, so if you have questions, you should make a noise because there's a really bright light right in my face. Okay.
So how long is the short project to failure versus a longer project that is 4 days? How long is it?
Right, the short project is 2 class days. So one class day to define the project and to get started, one night to go home and work on it if they want to, and then one day to try to put all the finishing touches on it, and then it's 4 full days over with a weekend in between, so they can really go home and work on it. So it turns out to be about 7 days work if they want to put in 7 days work, but it's 4 days of in-class time.
I've got one follow-up.
Yep.
Is it true, Ian, that MIT is your first choice?
Yes, that is true.
You're a senior.
So, I have a quick question. So using simulations and subsystems to actually create new products and existing materials to create new experiences, I think is fantastic. How do you make sure that people that actually do it understand the fundamentals and what's at play in those subsystems? So you're not just kind of taking off the shelf and seeing it, if it works, but not understanding how actually the piping works.
You mean for the people who are developing the games?
Correct. Yeah.
In a 9-day workshop, I don't have time to make sure that they are doing that. I trust that if they feel enough confidence to be able to build a system in 9 days that does something reasonable, then I trust that they have that existing expertise. If this were a semester-long project, then there would be a written portion of this that involves some layout of the underlying scientific concepts that they're trying to communicate with learning objectives. So in 9 days, I don't try to make them into instructional designers. I let them become familiar with the video game system. If it were a longer learning experience, I would definitely align it to make sure that they understand how to lay out the interactions that they want, how that corresponds to some type of a physical phenomenon. When they're visually representing it, are they communicating all the important matters? Like, if you wanted to visualize Kepler's law, then you could watch the area go around, but it's 9 days and I don't have time to get into the weeds with them about that.
Could you talk a little bit more about what the system that we created provides? Like, how does it make it easier to make these simulations as opposed to someone who from scratch? Are there certain what's included?
Yeah, so the benefits of this system are largely in a library that I created that allows you to interact with the Microsoft Kinect. So the Microsoft Kinect has an API that's available on the website, but Microsoft kind of stopped supporting it, as in they have dropped support for it. And it's really, really, really not user-friendly. And so what this enables you to do is you drag in one prefabricated game object, and then what you do is you have a drop-down menu in that little inspector plane, and you just select what joint you want that object to follow. So then in your game, you create a sphere, and it has this Kinect prefab on it, and you select left hand. Now, when you run your game, it just follows your left hand. There's no interacting with the bodies on the Kinect. There's no oh wow, there's another second body in the scene now. The list has changed. What am I gonna do? How am I gonna get the object that I need? How do I know that it's still the same person? The idea is that it hides all of that, making it much easier to just do that. Say you work on the Unity website you've seen their tutorials. They're not going to have anything on Kinect there. This is what enables you to be able to extend it beyond a mouse and keyboard.
Right. So in the workshop, we have students build on their laptops using a mouse, and anything that is a click and drag becomes a grab and move. So you can develop locally click and drag interactions and then port over to the system by simply switching out the mouse controller for this joint controller. So that's one huge thing. The other, same for the HTML5 simulation. So if you have something that's mouse driven on the web, it plugs right into this, and there's a web browser kind of behind the scenes that handles all of the interaction and display of the results. So yeah, you want a demo of that? I like it.
Yeah, that's awesome. You know what? I should turn on Wi-Fi.
Oh, yeah.
It's connecting to the web. You see?
Right. Yeah, so once he has Wi-Fi, then you'll be able to see the HTML5 one running live through the web. Yeah. Any other thoughts, questions, feedback?
Will you do this over just coming IAP as well?
I'm very tempted to. Staffing costs are a bit tricky, so I am trying right now to find funding in order to be able to support all of the staff and hardware that we need for it.
How expensive is one?
To pay for staff, I think it was 20,000 staff and hardware and everything like that.
So like, is it Unity software? Is that scalable or crazy expensive?
Unity you can use for free as long as you don't make money off of it. If you can make up to some amount,
Like 100,000 a year.
yeah, 100,000 a year, and you don't have to pay for it as long as you kind of attribute it. Right? Yeah, so it's totally they've made it very open and accessible for educators to use inside of the classroom. And any game that you create, if it does happen to start making more money, then you just switch the license and everything keeps working as it was.
Yeah, this is one of the web simulations. This is not ours. This is University of Colorado vet simulations, and like it plugs into any of them. So like my right hand moves the mouse, and then like by raising my left hand, I click.
How easy is it for other people to use this system if they wanted to?
To
Contact you?
to publish games on it, or
Yeah.
yeah, absolutely. Just contact us. Yeah, if you want to publish a game, let us know. If you want to have the system, kind of, if you want to figure out how to port your own version of this, let us know. Yeah.
Kyle, the 20K, is that necessarily a recurring cost, or do you need to buy new hardware?
I think that was much recurring cost for staffing. For 2 weeks. Well, maybe that was for both workshops. I don't remember. I'm spitballing that number. I know that there was a 20,000 that may have been for both workshops with staffing and hardware, because we ran concurrently an Arduino one. So I don't exactly remember the details off the top of my head. Yeah.
So 2018 is bringing a new generation of hardware motivated by VR gaming. Full body skeleton tracking, like the Kinect, hand tracked with full finger tracking. Do you have a wish list of, I wish we could have done X, but the tech wasn't there to support it, but as soon as it is, we're going to take advantage of this opportunity?
A wish list for what would go into a demo?
User interface sort of modalities.
Oh, yes. So the Kinect has terrible hand closure recognition. So even that this is a very intuitive interaction for a human, and even that is not reliable on a Kinect enough to use it. Yeah, I'm going to. We should talk after if you want to hear me ramble about ideas. Otherwise, I will subject a lot of people to a lot of rambling thoughts. I don't want to do that.
Well, maybe we should break for the demo part of it.
All right, sounds good. Yeah, so please feel free to come up and use it.
Okay, great, thank you. Yeah.